Okay, welcome to this video where we take a look back what we learned in this course, Calculus 1. Okay, so I'm going to discuss questions that will address all the concepts we learned so far in Calculus 1 course. Okay, so we'll discuss in this course mainly we discussed about derivatives, limits, mean value theorem, Rolle's theorem, and also we discussed integrations, fundamental theorem of calculus, and how we can use substitution to do integrations and so on. Okay, so first I'll take a time to write down major topics that we covered in this Calculus 1 course. Okay, so that will help you to kind of have idea what to study, what are the topics, the major topics, and so on. So if you see my questions that I create 13 questions, 13 problems to practice for your final exam. So I'm going to use those problems and tell you what concept, what topics that I include in each of these questions. What are the things that we're going to cover. Okay. So first you have to understand the idea of limits. It's very important. Left limit, right limit, continuity. So the other concept. Okay. So continuity or continuous functions. Okay. Continuity, and we talk about derivatives. Okay. Derivative actually defined as a limit. Okay, so remember derivative. Number 4, in the derivative we discuss power rule. Remember, so many rules we use to take the derivative of functions. If you have a product of functions, you use product rule, and if you have a quotient, you use quotient rule, etc. Okay, and also we talk about the derivative of ex, ln x function, sine function, cosine function, so many other things. Okay, cosine, sine, etc. Okay, and we talk about implicit derivatives as well, right? So implicit derivative, what else? Related rates, the derivative as a rate of change, and mean value theorem, intermediate value theorem, plus Rolle's theorem. Okay, Rolle's theorem. And also we learn how to use first and second derivative to discuss local max, mean, inflection point, concavity changing. The inflection point is the same as concavity change, where it changes concave up to down or concave down to up. So first and second derivatives. To draw graphs. Not only draw graphs, we also use them to do some optimization problems. So I can say optimization. We did a lot of optimization question in this course, and we talk about integration in general, right? So integration as antiderivative. We use basic integration, integration of trig functions, power ruling integration, substitutions, fundamental theorem of calculus, substitution we use, talk about Riemann sum. Riemann sum. How really integration develop? Like what is the concept of the integration? It can be understood as an area under curve. Okay, area under any curve. Right. So this is like kind of roughly like kind of idea or the topics that we discussed. As we go through each problem, you will see you kind of covering all the topics and kind of having idea about the course overall. Okay. So first question, I'm going to discuss something related to limits idea. Okay. There are the limits exist. What is the meaning of saying continues at a certain point and so on. So you can see the questions, all the questions on the screen when I explain. Take a moment, read the question, try yourself, find similar question that would really give you some confidence to do, well in the test or understand what's going on. So, first question is like a piecewise function given, okay? Given a piecewise function greater than x greater than or equal to, this is the function, it's a linear function. If it is less than 2, you have a parabola. You don't need to really draw the function to answer the limits. For example, the first question asks you find the limits. Find the limit when x goes to 2 from negative side, that's what it means, of fx. I'll show you how to draw it, but it says when x coming to 2 from negative side, which means less than 2, so you reach is like, you have a function, this is your x-axis, this is your 2, okay? So you coming to 2 from negative direction. That's mean you want to consider this function. So what happens if you plug 2 to that function? It will be 4. Okay, that's the limit of fx when x goes to 2 from negative direction. Because less than 2, this is how the function defined. Part B, limit of fx when you come to 2 from positive side. So when you come from this side, the function you are looking for is this. So if you plug 2 here, you can see you get 2 over 2 plus 3, it's also 4. So that means, doesn't matter when you, either way you come to 2, you get the same answer for the function, okay? The same limit. So the function look like this if you draw. This is 2, this is 4, I know it's a 4. This is only included at this point. So this is x over 2 plus 3. So greater than 2, so this is 3. So this is like how the function look like. Straight line. Okay, so let me draw it like this. So if you extended it, it's go through 3 actually. But you don't need to draw it. But if you extended it, the y-intercept is 3. The slope is positive half. So it's going like that. Less than 2, it's a parabola. But parabola start like 0, it's parabola, it's going like this, that parabola. Right. If the question asks f of 2, actually it's 4 as well. Because you can plug 2 here and get 4 there. Okay. The left and right limit is 4, and the function value also 4. Okay, you see that. And I can, for an example, in this problem, they will ask you, is f is continuous at 2? Yes, it is continuous at 2 because the function value is equal to the limit when x goes to 2. If you have same left and right limit, you can say the limit exists. Okay, the question really asks you what is limit of fx, x goes to 2. Then you can say it's equal to 4 because both the left and right limit same. If it is not same, you can say limit does not exist. This is part C. Since the limit and function value is equal, you can say the function is also continuous. Function is continuous at 2. It's not a question, but if it ask you a question like that, you can say yes, it is continuous at 2. Part B, limit fx when x goes to 3. Yeah, x goes to 3. So 3 is somewhere here. You're only looking at this function. So it's 3 over 2 plus 3. So it's like 3 over 2 plus 3. It's like a 1.5. So it's like a 4.5. It's 9 over 2. Yeah. 4.5. Okay. Clear? Okay. Right now, this is D. E. Limit of fx, x goes to 1. X goes to 1, you have to look at this function because it is the domain. So the domain for this one is less than 2. So it's just 1 to the power 2, which is 1. That's the answer. Okay. So extra question I can ask, is fx continuous at x equal to? Like I say, yes. The reason is limit of fx when x goes to 2 is 4 and it's equal to the function value at 2. Function value at 2 is also the same as the limit. Since it satisfies this condition, I can say it's continuous at 2. There's no break. There's no hole at 2. This function is stop at right here. The other function is start at the same point. Okay, right. So I think that's the idea of the limit, and that's really gives you the definition of the continuity. Okay, right. Continuity means the limits really tells you the graph has a hole or not, or jump or not. Because if there's a jump, left and right limit would not be equal to each other. Okay, right. So let's see the question number 2. Question number 2 gave you kind of limit finding the limits, determine the following limits. The first part A, limit of 2 minus square root of x over 4 minus x when x goes to 4. This is a little tricky when you plug, previously in the first question I can plug the value to my x, or I can replace my value with x, and I can get the answer, right? So without any indeterminate forms. So for example, if I plug 4 here, I get 2 minus square root of 4 is 2 over 4 minus 4. So it's like 0 over 0. This is like a indeterminate form. Like we can't determine what is the answer. 0, 0 is not defined. So we have a problem here. Okay? So we have a problem. What is the real answer for that? So then you have to use some algebraic technique. So kind of algebra to weigh out. So what we can do here, we can sort of take the conjugate of this. Conjugate, what I mean is, if you have minus 2 minus the square root of x, I take 2 plus square root of x. So I can multiply and divide by the same thing. And it would give you, because it's like a square difference, you can write it as a square difference because it's like a 2 plus square root of 2x, 2 minus square root of x. So I can write that 2 to the power 2 square root x to the power 2. Let me write it like one. So square difference of these two. can be written as this way. So bottom, I can keep it as it is, 4 minus x, 2 plus the square root of x. Okay, right. So now you can see this is 4 minus x that we can cancel out with the numerator. So I will write one more time. It's like 4 minus x in the numerator. Denominator also has 4 minus x. And I have 2 plus the square root of x when x goes to 4. So I can cancel that and then apply the limit. Because here we are not really plugging 4, we are really approaching or reaching to 4. Okay? So of course we plug x equal 4 if there's no trouble like 0 over 0. Okay? Of course, once I cancel that out, I can plug 4 here. So which is 1 over square root of 4 is 2, 2 plus 2 is 4. That is the limit. Okay? So initially it would not give you 1 over 4 directly. The reason is we have algebraic issue, we can't apply exactly 4 to the function. Okay? Function value at 4 does not define, but the limit define. Okay? Limit exists. Function value might not be exist. Because you can't plug 4, the denominator is 0. The 4 is not in the domain. Okay? But we can discuss what happens when x getting closer to 4. Right. Similarly, part B. So this is all question here. You can use the same technique. Okay. X cubed minus 1 when x goes to 1. Square root of x minus 1. Here also you can take square root, because if you plug 1, it's like 0 over 0 again. Okay. So I'm gonna take square root of x plus 1, multiply and divide. Okay. Multiply and divide. It's the same factor. Then you can see I can write this one as a square difference. The reason is it's square root of x minus 1, square root of x plus 1. Okay. Then this becomes x minus 1 and x goes to 1. But you may ask, okay, it's still not cancel out because this is square root of x square is x. That's okay. 1 square is 1. Okay. But you can't see any factors cancel out. But you can remember x cube minus 1 cube. It's like cube difference. 1 you can write as 1 cube. So it can be written as 1 x minus 1, x to the power 2, the product, I think it's like x plus 1. You can check. If you simplify that, you can get the x cube minus 1 back. Yeah, I can see that. Yes. So because of that, I can write now limit x goes to 1, x cube minus 1. I can write x minus 1, x to the power 2 plus x plus 1. And I have square root of x plus 1 also. Divide by x minus 1. Here. So x minus 1 cancel out. Now I can plug 1 to this, which gives you 3 times 2. 6. That's the limit. Okay. I know it has some algebraic algebra. You've been using algebra all the time when you simplify limits. Okay. So the way out is use some algebraic technique. The third question, part C, I give you a trig function, okay, trigonometric function. Maybe you can use double angle formula here. Let's see. Cosine 4x over x to the power 2. When you plug x equals 0, cosine 0 is 1. So 1 minus 1 is 0 over 0 if you plug 0. So it's 0 over 0 again. So you know cosine 4x can be written as 1 minus 2 sine square. If you have 2x, it will be x. It's a half of that angle. If you have 4x, it's 2x. So don't forget that, okay? So I'm going to plug that. Same question. X goes to 0. 1 minus this. So it's like you subtract this. So this become minus, this become plus. Okay, take your time. 1 minus of this. When you subtract this, 1 become minus 1, minus become plus. So 1 cancel out. So you can write limit. So this is the tricky part. You have 2 sine 2x, sine 2x. I write sine 2x 2 times. Because I have sine square. So I have x there and another x here. X to the power 2. The reason I write like this, I have a theorem sine x over x when x goes to 0 is equal to 1. I showed that in class using geometric approach. Remember, you don't need to prove it, you're going to use it. Sine x over x, when x goes to 0, it's 1. If you have 2x here, you have to make it 2x. So whatever, if you have theta here, it should be theta. Or if you have 5 theta, this should be 5 theta. So this is 2x, so I'm going to make 2 here. So I'm going to multiply that because I have to cancel out. And if I make 2 here, I have another 2 coming. So when x goes to 0, this part goes to 0. This part also goes to 0. It's basically 2 times 2 times 2, 8. That's the answer. Okay? That's how you get the answer. I know sometimes common mistake, you just keep x without making 2 and 2. You must make 2 because you have 2x. The angle is 2x, not x. Right. So I'm gonna do the last part, 4th question in this limit part. Okay. So this one probably the easiest one because it gives you, this is question number 2 part D, last one. Limit h goes to 0, 4 minus 2 minus h to the power 2 over 2h. Again, if you plug 0 for h, this is 0 is a 4, 4 minus 4, 0, 0 over 0, again undefined. Okay, so but this is, I think, easy because you just need to simplify 2 minus h square. If you square the first guy, it's 4. Twice of the product, it's 2 times h minus 4h, but you have minus here, it's plus 4h. H to the power 2, but you have minus here, so it's h to the power 2. So these 4 and 4 cancel out, that's the trick, okay? So now it's good. So 4 and 4 cancel out, so you have 4h and h to the power 2, you have 2h in the denominator. When h goes to 0, 4h and 2h you can simplify to 2. You have h to the power 2, if you divide by h, it's still h, 1h is available. When h goes to 0, it disappears. So the answer is 2 in this case. If you want, you can take h out and cancel out with the bottom, and you can see the same answer you can get. Okay? So that's question number 2. Determine limits. Okay? Third one, find the intervals in which each of the following functions continues. But I give you only one function. Okay? So because I used to give few questions using this, but in this case you have only one question. Determine which interval this function is continuous. This is what you want to think, number 3. So this is the question. So where this function is given, not the limit. So we can calculate the limit later. It's again piecewise function. The first function is a rational function. X plus 2. If x is not equal to 2, negative 2, okay, and it's equal to 1 if x equal negative 2. The reason is when x equal negative 2, you can't get the function value using this. So I define it separately. What happened to the function at negative 2? If you need to know what is the function value at 5 or negative 1 or negative 10, plug that number here to get the function value. You can get the function value for x using this, any value other than negative 2. But when you want to calculate function value at negative 2, you can quickly get it from using 1. Okay? Right, so that's the idea. So this is what you can see. So the problem is the problem happen at -2, because any other situation you can find the limit by just plugging the x value to the function here given in the first piece. Okay, so for an example, if you find the function limit at 3, you can plug 3 and get the value. So that's the value when you come into 3 from negative and positive side, so it doesn't change. So limit x is function value and limits are same. It continues at any point other than negative 2. So let's see what happened at negative 2. So when you come to negative 2, okay, let me see. So this is not equal to negative 2 when you come approach to negative 2. So I'm going to use this one because it's not an equal situation. So I'm going to use my original function, but I can factorize that. Can you see this? I can factorize like this. X plus 2, x minus 1. Those are the factors of my numerator. So I can cancel out with the bottom. So I can plug minus 3, I get minus 2 type minus 1. Minus 2 minus 1 is minus 3. So this is not equal to function value at minus 2. Function value at minus 2 is 1. So limit of the function when x goes to minus 2 is not equal to the function value. So I can say fx is not continuous at x equal negative 2. It's continuous. It continues negative infinity to negative 2, negative 2 to infinity. Anything other than negative 2, it's fine. But that's a jump at negative 2. The jump is from, like, I'm not going to draw it exactly, it's look like this. At minus 2, the function value is 1, but it's reached to negative 3. So function coming from here, and actually it's a hole, not a jump. It's going like this. This is your function fx. It's not exactly look like that, but I want to tell you when you come to negative 2 from left side or right side, you get the value negative 3. That's what you got here. But the function value really is sitting here. That means there's a hole here. That point is located at negative 2, 1. So that's the function value. Okay. Cool. Right. So we have some derivative problems. Okay. So I'm going to use product rule, quotient rule, power rule to do those 5 questions. Okay. So after complete these 5 parts of the question number 4, I'm going to stop the video and I make another video because it's too long. If I, do all the questions in one video, it's will be too long. So I will do first 4 problems and maybe the other 4 and so on. Okay. So let's make it like a 3 videos. Right. So this is my 4th question. Last problem for this video, number 1. Okay. Number 4. Find the first derivative. It's just first derivative. Fx part A. X to the power 2 plus 2x plus 1. X to the power 2 plus 5x plus 1 over x. 1 over x I can write like a minus 1. X to the power minus 1. It was 1 over x, but I can write it like a negative power. So then I take the derivative. I have to take the derivative of one of the thing first. I'm going to take the derivative of this, 2x plus 2, and keep the other one as it is. Clear? Plus, take the derivative of this and keep the other one as it is. Okay? I'm going to take the derivative of this, 2x, 5, and minus 1 come down and subtract 1 from the power. Remember, if you have x to the power n, the derivative is nx n minus 1. Okay? I take the derivative of the second factor and keep the other one as it is. And you can keep it like that. You don't need to simplify further because it's we are not going to use it to solve critical points or anything. We just apply the product rule for the product of 2 functions. Okay? Derivative of the first one, keep the other one as it is. Derivative of the second factor, keep the other part as it is. That's part A. Part B, it's a quotient rule. We've been exposed to this type of question many times. Actually, when we really do optimizations, when we practice like questions like finding local points, local maximum, local minimum, we use those type of derivatives again and again. Okay, right. So quotient rule. When you take the quotient rule, you write the denominator. You write the denominator and take the derivative of the numerator minus. Write the numerator. Take the derivative of the denominator. This is actually 2 times x to the power half, square root of x. So you can write 2, you take the power down, x, subtract 1 from the power. See, half take down and subtract 1 from half. That's the derivative of the denominator, and you square the denominator. So it's a 4x. Square the denominator, not take the derivative of the denominator. Okay, so I think that's kind of a mistake sometimes you do. So if you have a denominator over numerator over denominator, so derivative normally we define dn dash nd dash d square. D n dash minus n d dash and d square. Okay, that's good. Part C, we have a trig function. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tan is secant square. Derivative of 6 trig functions you must know, okay? Other things, products and everything you can create from that, basics. But you must at least know the derivative of basic 6 trig functions, okay? Of course, if you need tan, you can use tan is sine over cosine, so you can use quotient rule to get the derivative of tan, because tan is sine over cosine, it's a quotient rule. If you know sine, derivative of sine and cosine, you can get anything, okay? The function is here 1 plus tan x times cotangent x. Okay, so derivatives, you can use like a product rule. First one you keep as it is, take the derivative of cotangent. What is the derivative of cotangent? Cotangent is cosine over sine. You can use cosine over sine and use the quotient rule if you want, or 1 over tan. Cotangent is 1 over tan. So if you want to take the derivative of cotangent, you can take it like a, minus 1. Power you can take down. Tan negative 2 power. Tan x, what is the derivative of tan? We know it's secant square x. So this will be like minus tan is sine over cosine. Secant is 1 over cosine. Square actually. Wait a minute. Yeah, it's a power 2, so it's like going down, tan down, so it's like cosine square because it's like a 1 over tan. So 1 over tan is again cotangent. So cosine square over sine square. So you can see it's minus cosecant square x. Cotangent, if you take the derivative, it's minus cosecant square x. Okay. So normally students remember it like just cotangent has derivative minus cosecant square. If in case if you forget, use the basic definition and get that value. I use the power rule here, and of course you have to use the chain rule because you have to take the derivative of tan and multiply with that. Okay. Plus cotangent x times the derivative of this 1 plus tan, the derivative of 1 is 0. Derivative of tan, I really write it here over there, secant square x. That's the part C. Okay. Product of trig functions. Okay. D. Here we have quotient of trig functions. Sine x to the power 2, 3 minus 4 cosine x to the power 3. Remember, some of the, within product rule, sometimes we have to use chain rule. Similar when we work with quotient rule. Okay. So when you work with quotient rule, see, you write the denominator times the derivative of the numerator. So sine, the derivative is cosine x to the power 2, but you have to multiply with the derivative of x to the power 2. That's the chain rule. Okay, it's 2x. If you forget to do that, it's wrong. Minus sine x to the power 2, and you have to take the derivative of the denominator. Okay, so 3, 0, minus 4. The cosine has derivative sine, but minus, right? Minus sine, so it's become plus. So I can write 4 times sine x cube. The derivative of negative 4 cosine x cube is positive 4 sine x cube, but you have to deal with the x cube, so it's 3x to the power 2. And you take the entire things, divide by 3, 4, minus 4 cosine x cube square. It's pretty, large, because you just keep applying quotient rule plus the chain rule actually. Okay. And since you don't need to simplify, I think it's not a big deal. So, and also I will not give you, like in the final exam probably, I'll give you 2 or 3 questions look like this. It's not very, so probably when you practice, you really do like 5, 6 questions to get familiar with each rules. Okay. Product rule, quotient rule, power rule, chain rule. Okay. Those are the 4 basic rules to use. Last one is actually the easiest one. Number 4, E. So this one is just applying power rule and chain rule. So actually you take the power down, the derivative, take the power down, write everything as it is. That's the power rule. You subtract 1 from the power. So done with the power rule, and you go to the inside function and take the derivative of that. That's where you use chain rule. Alright, so that's the end of the first video. I'm going to start with question number 5, which has some interesting questions like implicit derivative, related rates, mean value theorem, Rolle's theorem, some integrations, some optimization problem, and etc. Okay, all right. So we'll continue from there.